Hello everyone and welcome to the second lecture of the logic part of Comp 0003. In today's lecture we're going to start looking at our first major topic, which is propositional logic. We'll look at that for probably 3 lectures. In propositional logic, the formulas are basically built up from variables standing for propositions, which are simple factual statements, and they're connected up together using logical connectives like and, or, implies, not, and so on. Although this logic is really very simple in many ways, it's also the basis for the logics that we'll go on to study in the remainder of the course. So it's really kind of fundamental building block of what's going on. Remember that I said that a logic has got really 2 main components, at least from the point of view of this course. First of all, a syntax explaining what counts as a formula of the logic, and then a semantics explaining how we should understand or give a truth value to formulas in the logic. So accordingly, the plan for today's lecture is going to be as follows. First of all, I'll introduce the syntax of propositional logic and explain how they correspond to English sentences. Second of all, I'll explain how the truth value of a propositional formula is determined by the truth value of its component propositions and the connectives that it contains. And finally, I'll give a very simple method for determining the truth value of a formula in propositional logic based on constructing its truth table. So I think we'll just go straight to the slides. Okay. So as the slide says, propositional logic is one of the simplest known logics, and it's in pretty much universal usage. The version that we are considering here is sometimes called classical propositional logic. In propositional logic, the way that we construct formulas is they are built up from atomic propositions or propositional variables using logical connectives. And although I think we've seen some of these already, let's go over them again now. So we have this symbol here, which stands for not, or sometimes called negation. This wedge stands for and, sometimes it's called conjunction. The V here stands for or, and is sometimes called disjunction. This arrow means implies, or in other words, A arrow B is read as if A then B, and it's called implication. And this double-headed arrow stands for if and only if, or meaning that 2 things are equivalent. So A double arrow B means A if and only if B. And this double arrow is sometimes called a bi-implication or an equivalence. As you would expect, negation is unary in that it takes 1 argument. So if A is a formula, then so is not A, whereas all the others are binary, meaning that they take 2 arguments. So for example, A or B, A implies B, A and B, so on. Now, at this point, you might want to ask, what are propositions? And while I'm not a philosopher, I think we can take a rough definition, which is to say that propositions are the smallest factual statements in an English statement, in an English sentence. And connectives are kind of words or phrases that connect propositions together. So examples in English are things like and, but, or, either, if, unless, except, and things like this. So let's take a simple example in English, the following sentence. If it's raining, I'll stay in and eat pie. Well, okay, we can definitely see that there's an if in there, and there's also an and. So there's 2 connectives in that sentence, and we also can think of, we can isolate 3 propositions. It is raining, I'll stay in, and I'll eat pie. Sometimes the exact proposition can't be precisely read off from the English sentence, but it's somehow implicit. So, for example, I'll eat pie is somehow got by by kind of extracting like that. So propositions are, it's raining, I'll stay in, and I'll eat pie. Of course, it's not the case that every English sentence can be interpreted as a collection of propositions connected by logical connectives. Things like questions, what's your name, is not a proposition, but on the other hand, if you reword it so that it says, I would like to know what your name is, well, in that case, that is a proposition. Or a command like, go away. Go away is not a proposition, but if you kind of reword it as, in my opinion, you should go away, and then that is, then the proposition is something about your own state of mind, and then it does become a proposition. So formally, let's do we'll define the syntax of propositional logic in the following way. First of all, we're going to need some variables standing for propositions. So I'm going to use generally capital letters P, Q, R, S, T, and kind of so on to stand for propositions. And these things are going to be called propositional variables. Now, to say what I mean by a formula of propositional logic, I'm going to give a grammar, or a grammar which might be called inductive or recursive, in that the right-hand side of the grammar is going to be allowed to mention things that occur already on the left-hand side. So let's just go ahead and see what I mean. So I say a formula A of propositional logic is either one of these proposition letters. So a single proposition letter by itself is a propositional formula. And this says that if A is a propositional formula, then so is not A. So a propositional formula is also given by applying the negation symbol to something that is already a propositional formula. Or if I have two things that are propositional formulas, then I can write their conjunction, A and A. Although I don't mean that they have to be the same. I don't mean that they have to be the same formula. I simply mean that they both have to have somehow the same type. So really, this grammar is defining a type of propositional formulas, and we're saying that the two arguments to the conjunction have got to be of the same type. They must also be propositional formulas. So another way of saying it is, if A and B are both propositional formulas, then so is their conjunction A and B. Now, I'm also placing these in parentheses. This is going to be so that formulas can be read unambiguously. Similarly, a propositional formula could be the disjunction of two propositional formulas with this or symbol, or it could be an implication between two propositional formulas, A implies B, or it could be an equivalence between two propositional formulas. So you see that these are exactly the connectives that I mentioned 2 slides ago. Now, although I've insisted here in my grammar that all formulas should have outermost parentheses around them, so parentheses around every sort of every connective, we can notice that the very outermost parentheses obviously don't add anything to how you read the formula. The formula is still unambiguous if you drop the outermost parentheses, so we usually do. So for example, rather than writing P implies Q or R all in brackets, I will usually drop these outermost brackets here and just write P implies Q in brackets or R. And by the way, notice that this is a very different formula, means something quite different than if I had put the brackets the other way around. The formula P implies Q or R in brackets is also a formula, but it definitely doesn't mean the same thing. Also, another kind of notational convention is that I usually won't bother to put any brackets around a negation. Negation somehow binds tighter than the other connectives or has greater precedence. So that means that, for example, when I write the formula not A or B, I don't mean not A or B. I mean that the not binds tighter than the or. So not A or B should always be read as meaning not A or B. So just a quick note here is that actually we can always write down for any given propositional formula, we can write it down also in the form of a syntax tree, which is completely unambiguous. So here's a propositional formula, which is P implies Q if and only if not P. Now we can write that as a syntax tree in the following way. So the root of the tree, the top level connective, is the if and only if, the by implication, because that's somehow the outermost connective of the formula. We could almost call it the main connective of the formula. So the formula should be understood, first of all, as a by implication, which has two arguments. One is P implies Q, and the other is not P. So if we look at its first argument on the left, well, that's an implication formula. And the implication formula is also has two arguments, which are simply P and Q. On the other hand, the right-hand argument of the by implication is not P. Remember that not is unary, it takes only one argument, so as we expect, it only has one child. So this formula is a negation at the outermost level, not P. So it's a not who with argument not P. And of course, not P is itself can be written as a tree whose root is not this second not, and with one child, which is again P. And this is completely unambiguous. Given any propositional formula, we can write down its syntax tree in a completely automatic way. We don't have to make any decisions. Now, one thing that I will definitely expect students to be able to do in this course is to be able to translate English sentences to propositional logic formulas. So the kind of technique for this is really to look at the sentence, first of all, identify all the propositions in the sentence, and then write down a propositional variable to stand for each of these. For example, I could write down the letter R, the proposition letter R, to mean the proposition, it is raining. And then you have to decide how the structure of the sentence should correspond to the logical structure of the formula. So in this case, if it's raining, I will stay and eat pie. So here I would say, okay, let's have propositions R for it's raining, S for I will stay, and P for I will eat pie. So, I mean, it seems fairly clear that the correct translation of this is if R, then S and P. So that's the translation here. So it's an implication at the top level. If it's raining, R, then in brackets, remember, we have then two things. One, I will stay, S, and two, I will eat pie, P. Okay, next example. You're getting in if you have a ticket. Well, okay, we can definitely isolate two propositions in this sentence. T, let's say, for you have a ticket, and you're getting in, and we could say, let's say G for that. But you can look at the structure of the sentence here. It says, you're getting in if you have a ticket. Well, another way of saying that is, I mean, actually, you could write it the other way around and say, if you have a ticket, then you are getting in. So really, the most natural way, I would say, of translating this sentence is simply as the implication, T implies G. Next example, you're getting in only if you have a ticket. Well, the propositions are the same, but now instead of if, we have only if. So really we're saying here that only people with tickets are getting in. But even if you do have a ticket, then that might not be enough to get in. It might be you getting in only if you have a ticket, but the bouncer might impose some extra conditions as well. But one thing that you can definitely say is, if you're getting in, then it must be the case that you have a ticket. There's no way you can get in and not have a ticket, which means that the translation of this formula is actually an implication the other way around. If you're getting in, then you must have a ticket. Okay, and here's one more example. you're not getting in unless you have a ticket. Now, although there's many ways of potentially translating this, it actually is, it actually is sort of saying, it's actually saying more or less the same thing as the previous formula. It's kind of saying, you're not getting in unless you have a ticket. If you don't have a ticket, then you are not getting in. So one way of kind of translating this is, if you don't have a ticket, not T, then not G, you're not getting in. If you don't have a ticket, then you're not getting in. I think that's a reasonable way of translating you're not getting in unless you have a ticket. Or, and we'll see that this is actually an equivalent formula, we can say that actually there are two things that could be the case. Either you're not getting in, or you do have a ticket. So either not G or T. And we'll see at some point soon that these are actually the same thing. Okay, let's even do one more. So here's a complicated sentence. If it's raining, I'll either stay in and eat pie, or take an Uber to the pub, provided that's not too expensive, in which case I'll get the bus there instead. So what are the propositions here? Well, okay, so the propositions include it's raining, I'll stay in, I'll eat pie, I'll take an Uber to the pub, or I'll get the bus to the pub, and there's also a thing of the Uber is too expensive. So I would translate that as the following, in the following way. So if it's raining, then all the rest of this is the case. So if it's raining, then either I'll do something or I'll do something else. So the main argument of the conclusion of the implication is a disjunction. So what are the two possibilities? Either I'll stay in and eat pie, okay, S and P, and then we have two different cases. If it's not too expensive, I'll take an Uber to the pub, and if it is too expensive, I'll get the bus to the pub. So I'm going to translate this as a conjunction of not E, if it's not too expensive, if and only if I take the Uber to the pub, and it is too expensive if and only if I take the bus. I think because, of course, we can't have E and not E at the same time, this would actually turn out to be the same if I'd written these two by implications as simple left to right implications. But we can, but I think here it's not too serious, and I think the meaning of the formula is the same in either way. Okay, so at this point, I would like us to just go back and remember our two key classical Aristotelian principles from the previous lecture. The first being the law of non-contradiction. Two directly contradictory statements, which is to say A and not A, cannot be true at the same time. Remember, I'm writing this turnstile symbol to mean it is a law that. So it is a law that not A and not A. And that's true for any propositional logic formula A. For no propositional logic can we have that P and not P holds. And secondly, the law of excluded middle, which says that every statement is either true or false. It is a law that either A or not A for any statement A. So in other words, in classical propositional logic, every statement is either true or false, so it has a truth value of either true or false, and it is never both true and false by the law of non-contradiction. Now this gives us the idea of a valuation in propositional logic. So given some propositional logic formula A, let's write the letter L to mean the set of all the propositional letters that are occurring in that formula. So if I write the formula R implies S and P, then by L I really mean the set consisting of the letters R, S, and P. Also, because we're computer scientists, instead of writing true and false all the time, I'm going to use the value 1 to stand for true and the value 0 to stand for false. This is also exactly what is done in electronics, so it makes sense from that point of view. And by evaluation, V for A, so I say, I talk about giving a valuation to a propositional logic formula A, then what I mean of that is take all the propositions in A, so for example, R, S, and P, and for each one of those, I would like to interpret them as having either the truth value true or the truth value false. So in other words, you could think of it as an assignment, a function V from L into the set 0 and 1. So when I write function notation like this, I mean the function is called V, and it has the type. The colon means it says this is the type of the function, and this is a function from L. That's the domain of the function. So the arguments of the function are things in L, and the values it returns are 0 and 1. Well, are either 0 or 1 for each argument. So for example, I could think of a valuation that sends R to 0, S to 1, and P to 0. Next, I'm going to explain how, given a valuation for A, which just tells you whether the propositions in the formula are true or false, then that actually determines completely whether or not the actual formula is true or false overall, and that's determined by the connectives. Okay, so let's start with the negation. Negation is a pretty simple case. Well, negation just flips the truth value of its argument. So not A is true if and only if A is false. By the way, because if and only if is a bit of a mouthful or a lot to write down, quite often we write the word if with two F's to stand for if and only if. So in other words, if A is false, then not A is true. And if A is true, then not A is false. And that can be written down in the following way in the table. So here I have formula A and formula not A, and then the two possible truth values for A. Remember, of course, there are only two possible values, true or false. So if A is false, then not A is true. Remember, 1 for true, 0 for false. And if A is true, then not A is false. Easy. Next, we have conjunction, and that's a similarly easy case. A and B is true if and only if both A and B are true. The conjunction can't be true if neither of A and B hold, and it can't be true if only one of them holds. So here, I've written a table. It's a bit larger. It has 4 lines because we have to consider all possible truth values of A and B. So obviously two truth values for A, and for each of these, 2 possible truth values for B. So if A and B are false, then A and B is false. And if A is true and B is false, then A and B is false. If A is true and B is false, then A and B is false. And if A and B are both true, then A and B is also true. So A and B really means exactly what you think it means. It means both A and B at the same time. Next, let's move on to disjunction. So A or B is true if either A or B is true. But in logic, it's important to say that or is inclusive. So A or B means A or B or both. Let's look at the truth table. So again, we have all the possible truth values of A and B, and we see that A or B is false when A and B are both false, and in all other cases, either where B is true, or where A is true, or where they're both true, then A or B comes out true as well. So this is sometimes a bit different than how we mean it in English, where sometimes we mean or to mean one or the other, but not both. You say that I'm either walking or I'm taking the bus, but you don't mean that you're going to do both. But here, it's fine. If we wanted to write down the exclusive version of or, meaning A or B and not both, well, we could actually express it using the formula A or B and not A and B. And you can check that. Oh yeah, okay. So that's exactly what I wrote down on this slide here. So Also, as a kind of consequence of this, and again, we can check using the truth tables that we have already, that not A and B is exactly the same as not A or not B. And that's true, but I mean, you can see that it makes sense intuitively, because if it's not the case that A and B are both true, then it must be the case that at least one of them is false. And likewise, if at least one of A and B is false, meaning not A or not B, then it must be the case already that they can't both be true. So if you have not A, then certainly you have not A and B. And the same thing if you have not B. So for that reason, you get the equivalence. And we have a similar equivalence connecting or an and negation, but in the other direction. If I have not A or B, then that must be the same as to say not A and not B. If it's not the case that you have either A or B, then it must be the case that you don't have either of them. Actually, you can see that just from the truth table here. If A or B is false, there's only one possibility, which is that A and B are both false. Similarly, if you have not A and not B, well, then you just read in the other direction. Then you have that A or B must be false as well. In other words, not A or B. Okay, and now we come to the sort of the elephant in the room, which is implication. And many people, I would say, find this somewhat counterintuitive, to say the least. And so I think we'll maybe go back and have a bit of a chat about it. But let's have a look at the truth table first. So, I mean, just from a sort of natural language reading of implication, it's simple enough. The formula A implies B means that if A is true, then B is true as well. So the truth table is as follows. Well, let's look at the third line first, because that's probably the hard, sort of engenders the least amount of disagreement. Well, if you have that A is true, but B is false, then A implies B is also false. You can't, I mean, that makes sense, right? Because you say, well, I can't possibly have that if A then B, because I have A and I don't have B. So A implies B is false in that case. Now, interestingly, the truth table for implication means that A implies B is actually true in all other cases. Now, I mean, we'll have a bit of a chat about why in a second. Just for the following moment or two, just accept it for now, and then we'll go back and try to justify it in a minute. So, in particular, you can see just by looking that the following pairs of formulas are equivalent. A implies B actually means exactly that not A or B. So you see in the two cases where B is true, then A implies B is true. And in the two cases where A is false, then A implies B is also true. And that rules out, then that's actually all the cases in which A implies B is true. Similarly, not A implies B means exactly that A and not B. So if A implies B is false, not A implies B, then you could read from the truth table that we have A and not B. And similarly, going in the other direction as well. So this is all very strange, and so we should try and talk about it, I think, now in a little bit more detail. So let's go back to the board. Hello again. Okay, so you see that on my whiteboard here, I've written up again the truth table for implication that we saw on the last slide, and I've also added in a column for not A or B, because I want to show that the truth tables are the same. Let's just go over that briefly. In the first two lines, we have that A is false, meaning that not A is true, and that and so forth, and so certainly not A or B is true. In the fourth line, we have that B is true, and therefore not A or B is true again. So that takes care of three of the lines. And for the third line, we have that A is true and B is false. And that means that we don't have not A and we don't have B either. So certainly not A or B can't be true either. So that shows you that for sure that the truth table for A implies B coincides with the truth table for not A or B. But of course, it doesn't explain in itself why the truth table for implication should look like that, and why this is the right truth table somehow, and other truth tables that we might think of for it are kind of wrong. So I thought that I wanted to try and give some intuition, sort of philosophically, for why that kind of might be the case. I think the easiest way to start is with the third line here, where A is true and B is false. Then I think probably the intuition is quite clear. A implies B means that if we have A, then we have B. But in this line, in this situation, we do have A, which is supposed to be the condition for B to hold somehow, but we don't have B. So, for example, you can see in a video that I'm wearing glasses, and we know, so that's a true A, and we also know that the moon is not made of cheese. So if I say the moon is made of cheese, that's a false statement, so that's an example of our B. So if I make the statement, if I'm wearing glasses, then the moon is made of cheese, I mean, I think it's quite obvious that that is a false statement. It's false because I am wearing glasses, but the moon is definitely not made of cheese. You can't say if one, then the other, because you have one, but not the other. As for the other three lines, I think the best way to do it is actually to separate into sort of two further cases. We can see that the fourth column indicates that A implies B could be divided into two cases, which is one, not A. There's a case where A is false, but A implies B turns out to be true. Why should that be the case? And the other is the case where B is true, which is actually lines 2 and 4 in the truth table. So why should A implies B be true when B is true? So let's do that second case first, the case when B is true. So as an example of our true statement, let's take again the statement that I'm wearing glasses. And as our A, since A could be false or true, let's take a statement whose truth value you don't know. So let's take the statement, for example, I am wearing shoes. From this video, you won't be able to tell, I think. No. And but for sure, it's going to be one or the other. So I can say, think about the statement, if I'm wearing shoes, then I'm wearing glasses. Now, that's a true statement, whether or not I'm wearing shoes, for the simple reason that I am wearing glasses. If you suddenly discover that I'm not wearing shoes or that I am, then you'll say, well, you're still wearing glasses either way. So somehow, once you know something that's true, then it's already implied by any other statement. So the fact that I'm wearing glasses in this video now is true, and will always be true, no matter what other conditions obtain. So when B is true, then A implies B is true for whether A is a true statement or a false one, simply for the fact that you know already that it's the case that it holds. Now, think about the statement, the case when A is false. In other words, we have not A. So, for example, we know that the moon is not made of cheese. So the statement, the moon is made of cheese, is the example of a false A. On the other hand, we can see that in the case where A is false, B could be either true or false. So let's again take the statement that I'm wearing shoes. Now we can think about the statement A implies B, meaning if the moon is made of cheese, then I am wearing shoes. Now, why would that be a true statement? Since you don't know whether I'm wearing shoes or not, and the moon is definitely not made of cheese. So what does it mean to say that if the moon is made of cheese, then I'm wearing shoes? It kind of seems like an absurd statement in some ways. But think about it in the following way. We know that the moon is not made of cheese, that A is false. So we say, if the moon is made of cheese, then something else. Well, if the moon is made of cheese, then since we already know it's not made of cheese, we would be in a situation where the moon is made of cheese and is not made of cheese. In other words, a contradiction. Now, we already know our law of non-contradiction that situations in which contradictions occur cannot happen. What we are describing there, the kind of hypothetical of the implication, is an absolutely impossible situation. And it's the case that, in an impossible situation, we can correctly make any other statement or make any assertion B simply for the fact that we know that actually it is impossible. Since we're talking about a situation that can't happen, and in an impossible situation, everything is true. It is it's almost true for the same reason that the statement, all the unicorns in my office are blue, is a true statement. All the unicorns in my office are blue, is a true statement for the simple reason that there are no unicorns in my office. So when I say all, I mean all of the things in an empty set. If you were going to try and say it's false that all the unicorns in your office are blue, James, you big liar, well, then you would have to show me a unicorn that is in my office and that is not blue. And of course, you won't be able to find one. So the only possible conclusion is that all the unicorns in my office are blue is actually a correct statement. For the same reason, if I kind of say, in an impossible situation where I have a contradiction, then I'm wearing shoes, is a correct statement or true statement for essentially the same reason. I'll say that it's true in this situation, which is absolutely impossible. Or the set of situations in which this can possibly happen is actually the empty set. There are no such situations. For the same reason, by the way, it would also be correct to say that if the moon is made of cheese, then I'm not wearing shoes, or any other statement that you can think of. So I hope this has kind of helped to clear things up a little bit and has not simply made things worse. I think there's also like a little note on the Moodle page where I try to explain from a technical point of view why you also want A implies B to be defined in this way, because it helps, it makes all the laws that you want to work. So for example, you definitely want B to be true in all the situations where you have A and A implies B. I mean, for sure, if you have A and A implies B, then you need B to be true as well. So that justifies, for example, the fourth line where you have A and you have A implies B. And so you definitely want B to be true here as well. Okay, let's move on. Okay, so lastly of our connectives, we have equivalence or by implication, the double-headed arrow. So A, if and only if B, means that A is true if and only if B is true. In other words, A and B share a truth value. So if A is true, then B is true, and if A is false, then B is false, and vice versa. So that gives us the following truth table, where if A and B are both false, then A if and only if B is true. If A and B are both true, then A if and only if B is true. And if one of A and B is true and the other one is false, then A if and only if B is false. So in other words, it really does mean that they share a truth value. Now, we can say that there are some kind of equivalences we can write down straight away. And they're kind of the ones you would expect. So A if and only if B has the same truth table as you can see by constructing it as A implies B and B implies A, and it's also the same as saying either A and B or not A and not B, and that's really easy to see. You can just read it straight off the truth table. So A and B is this fourth line, and not A and not B is this line where A and B are both false. So easy peasy. Next, I want to introduce a notion of satisfiability and validity. So hopefully you've kind of seen that since evaluation gives a truth value to all the propositional variables that occur in a particular formula, and we have the tables that we've seen in the previous few slides explaining how to get the truth value of a formula involving a connective from its components, then hopefully you can see that given any valuation for a formula, so we interpret the propositions as true or false, then we can figure out whether the entire formula comes out true or false as well, just by constructing the relevant line of the truth table. So I'm going to write this symbol, the kind of double turnstile, and I'm going to usually say satisfies. V valuation V satisfies the formula A to mean that A is true in the valuation V. In other words, when we look at the corresponding line of the truth table, then given the values of the propositions given by V, then A turns out to be true. And if V does not satisfy A, so A turns out to be false, then I'll write this notation with a sort of bar through the double turnstile. V doesn't satisfy A. So a formula is called satisfiable if V satisfies A for some valuation V. In other words, that means that there is some way of assigning truth values to the propositions in the formula such that the entire formula turns out true in at least one line of the kind of truth table. And it's called unsatisfiable if you can't do that, if there's no way of making it true. If it always comes out false no matter what, in other words, if all lines of the truth table turn out 0, then it's called unsatisfiable. And this notion has a dual, which is called validity. A formula is said to be valid if no matter what valuation you take, so for all valuations V, the formula A turns out to be true. So every valuation satisfies the formula. V satisfies A for all valuations V. If, on the other hand, it doesn't satisfy, V does not satisfy A for every valuation V, in other words, if there's at least some way of making it false, then it's called invalid. By the way, it's quite easy to prove, and I would like you to try this as an exercise, that a formula A is invalid if and only if not A is satisfiable, and in a kind of similar vein, the formula A is unsatisfiable if and only if the formula not A is valid. By the way, just a little tip about proving things. Whenever you're asked to prove an equivalence like that, there are really two directions to prove. So let's take this this first part. Well, to prove this, I would kind of start by assuming that A is invalid and show that then not A must be satisfiable. That's one direction of the equivalence. And then I do it the other way around. Now, for the set, assume that not A is satisfiable, and go on to show that A itself must then be invalid. So a very typical thing that I might ask you to do in this course is to give you some propositional logic formula and then ask you to tell me whether or not it is valid or whether or not it is satisfiable. And a fairly easy way to do this is just to construct the truth table for the formula. That's not really viable when you have a lot of different propositional variables, because if you have n propositional variables, then the truth table will end up having 2 to the power of n lines. It's not a very efficient way of doing things because the truth table becomes quite big quite quickly. But for small formulas, it's no problem at all. So for example, let's take the formula A implies B. Okay, here that I'm thinking that of A and B as being propositions, but it doesn't really matter, since we know that every formula is going to be either true or false. So we can just consider all the possible values of A and B. So here, as expected, the truth table has 4 lines for all the possible truth values of A and B. And since the formula's kind of got 2 components, or actually, 2 connectives, first of all, I've written down the truth table for A implies B, and then by looking at the lines for A and A implies B, I can construct a table for A implies B. So A implies B should be true whenever the left-hand side A is false. So the first 2 lines, A is false, which means that A implies B turns out to be true. In the third line, we have A, but we don't have A implies B, so A implies B turns out to be false. And in the last line, we have that A implies B is true, which means that A implies B turns out to be true as well. So in fact, you can see that A implies B has exactly the same truth table as A implies B. So those two formulas are in fact equivalent. They have exactly the same truth table. And it makes sense as well, because somehow if you think that A implies B means if you assume A, then B is true, well, then this really says it doesn't matter whether you assume A once or twice. In other words, assuming it twice is the same thing as just assuming it once. So if A, then B is exactly the same as saying if A, then B. By the way, looking at the truth table, we can say that the formula is certainly satisfiable because at least some rows of the truth table turn out true, 1, but it's not valid because they don't all turn out to be 1. So we can say it's, or another way of saying it is, it's an invalid formula because there's some way of making it false, but it's not unsatisfiable either because it's not the case that there's no way of making it true. Oh yeah, okay. And so here's the remark which I made already, that these two things have got the same truth table. Let's take another example, again with just two variables. A and not A implies B. Now, by the way, this is basically the principle of explosion, which I kind of referred to in the little segment I did before, where this formula basically says that in a situation where you have a contradiction, A and not A, then B, for any B that you like. This kind of says any statement holds when you have a contradiction. And so here again, I've decided to break the formula down. First of all, to construct the truth table for A and not A, which is the left-hand side of the implication. And of course, A and not A comes out to be false in in all possible valuations. Here you have we have that A is false, which means we don't have A, so we certainly don't have A and not A. And in these two lines we have A is true, which means we don't have not A, so we don't have A and not A. And since A and not A is always false, by our truth table for implication, A and not A implies B always is true, and it doesn't matter the truth value of B at all. So in fact, this formula is valid. No matter how we interpret A and B, the formula A and not A implies B always comes out as being true. So it's a valid formula. Sometimes we would refer to valid formulas as tautologies. And by the way, as expected, the formula A and not A is unsatisfiable. There's no way of making a contradiction true in any situation. Okay, that's pretty much it for lecture 2. Thank you for listening. In the next lecture, we're going to stay on propositional logic, and I'll show you how to do things in a slightly faster way without going through truth tables by relying directly on equivalences in propositional logic to rewrite formulas. And we'll probably chat about some other things too. So until next time, take care.